We have a mass of 2.5 kilograms sliding on a flat, smooth track with an initial speed of 8 meters per second. Block slides up a rough, long incline that is 10 meters long and has a vertical height of 2 meters. And onto another flat, smooth track. The block's final speed is 4 meters per second. What is the magnitude of the frictional force? Right? We're going uphill. That means we're going to have some kind of height. Oh, look, it tells us there's a height there. Whenever we see a height, we're thinking there's probably some conservation of energy stuff happening here. But let's get to it. In the beginning, what kind of energy do we have? Well, what is the beginning? What is the end? Here to here? Can we go here to here? We're obviously going to be losing some energy to the environment here through a dissipated energy, like thermal, because there's friction involved. How do I know there's friction? It says it's rough. So whatever energy we have in the beginning is not going to equal the energy that we have in the end, all the way at the end. Instead, there's going to be some missing energy. So let's go ahead and look at, in the beginning, what kind of energy do we have? We have kinetic energy, right? And we'll say this is our beginning, step 1, step 2, and step 3. From 1 to 2, in the beginning we have kinetic energy. At the end of 2, we have gravitational potential energy, and we have kinetic energy. And remember, it was a rough surface. So we have energy lost by friction, which is our dissipated energy. Dissipated energy, remember, is our frictional force times displacement. Wait a second! That's what the question's asking us for. It's asking us for frictional force. That's it. All we have to do is plug in 1/2 mv squared equals mgy plus 1/2 mv squared. And solve for friction? That's pretty cool. Let's see if we have enough information. Half of m, 2.5, so that's going to be, we're going to have to just be very careful here. 1/2, 2.5. The initial velocity, use lots of parentheses here, is 8 squared, don't forget the squared, equals, let me take a step back, because this is going to get real messy. And my algebra is not so great, so let me make it easier on myself. Ready? I'm going to just solve this equation for my dissipated energy, because that's frictional force. So when I do that, and I subtract Ug at the top here, plus my kinetic energy at the end of 2, then I'm going to get Ed equals Ki minus Ug plus minus Kf. Okay. Now that's going to work in my favor in just a second. So let's go ahead and expand out all of these. So we have 1/2 mass, which is 2.5, times my initial velocity squared, 8, minus my mass, which is 2.5. I'm not going to have mass in all of these terms, am I? Because frictional force doesn't have mass in it, so I can't just cancel out mass. mg, let's go ahead and 10, and then my height, 2, minus, just bracket that all up, keep it all nice together, 1/2 of 2.5, times my final velocity, which is 4 squared. Right? Right. Give me a second, let me plug this in the calculator. And I'm back. Turns out half of 1.25, or half of 2.5 is 1.25. 8 squared is 64. all of this equals 80, 50, and then this equals 20. 80 minus 50 is 30 minus 20. So my dissipated energy is equal to 10 joules. That's not what we're asked for, is it? No, we're asked for the frictional force. So remember, frictional force times displacement, if we divide out displacement from each side. The total displacement that we have traveled was given to us as 10, divided by 10. So all of that to find out our frictional force equals 1 Newton. That seems reasonable. It's a really small frictional force. I like it.